Okay, so the last video for chapter 7 looks at Hess's law and then heats of formation. So Hess's law first. I have to say, I always thought Hess's law problems were really fun, and sometimes students have a really hard time with these, and I'm not 100% sure I understand why, so I'll do my best. What happens here is, and we saw this in the last video with the ozone and oxygen reaction, we're going to have given equations with enthalpies known. So we'll have a reaction and the enthalpy for that reaction, and another reaction and the enthalpy. And what we're going to do is try to figure out, using those enthalpies, what the heat of this other reaction would be, using kind of the pieces that we have here. And so what I kind of look at first is, when I look at my given equations, I try to look for unique substances in the given equation. So for example, in my target equation, I need methane on the reactant side. And when I look at my first reaction, there's no methane. But when I look at my second reaction, I see methane and it's on the reactant side. So I'm just going to call this reaction 1 and reaction 2. All right, so the methane here, I'm going to use reaction 2, right, because it's coming right from reaction 2. And the other thing I notice is, in reaction 2, I only have 1 methane, but I need it to have 2. So what I'm going to do is take reaction 2 and multiply it by 2. All right, so let me do that here. All right, so reaction 2 times it by 2. I get 2 CH4s plus 4 oxygen. On the product side, 1 CO2 becomes 2, and 2 waters becomes 4. So I've just taken that equation and multiplied everything through by 2. And so something we talked about on the previous video is that if this methane combustion reaction releases 890.3 kilojoules for 1 mole of methane, if I do the same reaction but for 2 moles of methane, I'm going to multiply that delta H by 2. I'm going to get twice as much energy released, right? Because I have twice as much methane. And so that's rule number 1. If you multiply through a chemical reaction by some whole number n, then multiply delta H by n. So we multiplied through by 2, multiply delta H by 2. 890.3 times 2. This means this enthalpy of this reaction is negative 1780.6 kilojoules. All right, so when I look at this equation, that's going to give me the methane that I need and the water that I need, right? So those are going to be taken care of. Now what I need is oxygen on the reactant side and carbon monoxide, not carbon dioxide, on the product side. Okay, so what I can see is oxygen looks okay except for the coefficient, but I want CO, carbon monoxide, in my target reaction, not carbon dioxide. So then I look at my reaction 1. Remember, look at unique substances. So like oxygen's not unique, it comes from both reactions. The carbon monoxide, however, comes from this first reaction. So carbon monoxide here is going to come from reaction number 1. So carbon monoxide is going to come from here. Number 1, is it on the correct side? No. In reaction 1, it's on the reactant side. I need it to be on the product side. So I'm going to take reaction 1 and I'm going to have to reverse it. Then the other thing I notice is I only have 1 mole of carbon monoxide in reaction 1. I need 2 in my target reaction. So I'm going to reverse it and I'm going to multiply by 2. All right, so here's what I'm going to do. I'm going to take reaction 1 and I'm going to reverse and then multiply by 2. So the carbon dioxide that was a product now becomes a reactant. The oxygen that was a reactant is now going to become a product, and the carbon monoxide also going to become a product. So the products become reactants, the reactants become products, and the delta H is going to just change the sign. So if you reverse a chemical reaction, just reverse the sign of delta H. And we talked about that on the last video. It makes sense that if I take carbon monoxide to carbon dioxide and release 283 kilojoules, going in the opposite direction means I'm going to have to absorb 283 kilojoules. All right, so I flipped the reaction. That was the first thing we said to do. But then we also needed to multiply it by 2. So if I multiply 1 times 2 for carbon dioxide, I get 2. 1/2 times 2 means that that's going to become a 1. And 1 times 2 means 2 in front of the carbon monoxide. And that delta H here, we're going to multiply it by 2. So 283 times 2 is 566.0, kilojoules, keeping my 4 significant figures. All right, so now what I should have is if I take these two equations that I had, these were my given equations, I manipulated them. Now what I'm going to do is add them together. So if I take all of my reactants, I've got 2CH4 plus 4O2 plus 2 CO2s, and then I'm going to take all of my products. I've got 2 CO2s, 4 waters, 1 oxygen, and 2 carbon monoxides. When I add two equations together, I'm going to add the 2 delta H's together. So my delta H here would be the negative 1780.6 added to the 566.0. So 566.0 added to a negative 1780.6, I get negative 1214.6 kilojoules. So that would be my new delta H. Now, does it look exactly the same as my target equation up here? Well, I've got my 2 methanes. Now let's look at the oxygen. I have 4, but I should only have 3. Well, I have 4 on the reactant side, and I have 1 on the product side. So I'm going to subtract 1 O2 from both sides. So the 4 became 3. All right, so now that works. The carbon dioxide shouldn't be here on the reactant side. When I look at it, I've got 2 carbon dioxides on the reactant side and 2 on the product side. So I'm going to reduce by subtracting 2 CO2s from both sides. I got 2 carbon monoxides, that's there, and the 4 waters, that's there. So now I have my target equation, right? I've got the 2 methanes plus 3 oxygens to make my 2 carbon monoxides and 4 waters. And I just took these 2 adjusted delta H values and added those together. So negative 1780.6, and then added to a positive 566.0, I get a delta H here of a negative 1214.6 kilojoules. All right, so that would be my delta H for that new reaction. So again, what we're doing here is we took equation 2 and we just multiplied it by 2. So we took that delta H and just multiplied it by 2. The first reaction, we reversed it, which means we changed the sign. Negative became positive. And then we also multiplied it by 2, so multiplied the delta H by 2. All right, so let's try another one. This time we've got 3 equations given, which looks like it might be harder, but again, always look for the unique substances. So I like to call this equation 1, 2, and 3, just so I can kind of keep track of it. So first thing here, I'm looking at ethene. And ethene shows up in the first reaction, not in the second, not in the third. So I'm going to use, in order to get my ethene, I'm going to get that from reaction 1. What I look at is it on the correct side? Yep, it's on the reactant side. Does it have the right coefficient in front? Yes. So reaction 1, no change. I'm just going to rewrite it. C2H4 plus 3 O2s to make 2 carbon dioxides and 2 waters. And that delta H value, negative 1410.9. All right. Now, the next thing I've got is the H2. All right, no H2 in the first reaction, no H2 in the second reaction. Let's look at the third reaction. Here it goes. So the ethene came from reaction 1. The hydrogen is going to come from reaction 3. Is it on the correct side? Yes. Does it have the correct coefficient in front? No. I want half as much. So I'm going to take reaction 3 and I'm going to multiply it by a half. So 2 hydrogens becomes 1 hydrogen. The oxygen 1 is going to become a half. And on the product side, instead of 2 waters, I'm just going to have 1 water. So the delta H, I'm going to multiply that by a half. Right? So the sign will stay the same. It'll stay negative. But 571.6, divide that by 2, I get negative 285.8. All right, so we took care of the hydrogen. Now for the ethane, that's coming from reaction number 2. So first thing is it on the correct side? No. All right, I'm going to have to take reaction 2, I'm going to have to reverse it. All right, I need the ethane to go to the product side, and instead of 2, I only want 1. So I'm going to have to reverse it and multiply by a half. So my product, carbon dioxide, becomes my reactant, but half as much would be from 4 to 2. Instead of 6 waters, I'll have 3 waters. And then on the product side, my reactant of 7 oxygens becomes 7 halves. And instead of 2 ethanes, I'm only going to have 1. So now what do I do to that delta H? I'm going to reverse it, so I'm going to change the sign. And then I'm going to also multiply it by a half. So I've changed the sign, 3,109.4, divide that by 2, and I get a positive 1,559.7. So when I take my new equations and add them together, hopefully I'm going to get the same as my target equation up top, the ethene plus hydrogen to make ethane. So some things should be canceling out here. So I see the 2 carbon dioxides here on the product side and here on the reactant side. So those will cancel out. When I look at water, I've got 2 plus 1, so 3 on the product side, plus another 3 on the reactant side. So 3 and 3 cancel out. So 3 on the products, 3 on the reactant side. With the oxygen, I have 3.5 oxygens, which matches the 3.5 on the product side. So 3.5 oxygens on both sides goes away. And then what do I have left? I have the ethene reacting with hydrogen to make the ethane. So I have my target equation. What happens to delta H? I'm going to add everything together. So I've got negative 1410.9 added to negative 285.8 added to 1559.7. So what do I get? So 1559.7, negative 1410.9, and negative 285.8. And I get a delta H here of negative 137.0 kilojoules. And since we're adding, we're going to keep that same decimal place, so take it to the tenths place. So Hess's law just takes a little practice. You're given some target equations, or given equations, excuse me, and you want the enthalpy for a target, right? We want to know the enthalpy of that reaction. When you look at these, go through and find the unique substance. Like the ethene only comes from this first equation. All right, so we're going to use the reaction 1 to get the ethene. Is it on the correct side? Yes. Is it have the correct coefficient in front? Yes. Those are your 2 questions. So that means I'm just going to rewrite it and not change delta H at all. Then when I looked at reaction 2, the ethane would produce the ethane on the product side. That's where I'm going to get it from, but it's on the wrong side of the equation. It's a reactant. I need it to be a product, so I'm going to have to flip the reaction, meaning I'm going to change the sign of the delta H. And instead of 2, I only want 1. So I'm going to have to cut this in half. So when I rewrote it, the 4 carbon dioxides cut in half became 2. The 6 waters became 3. And then my reactants became products, again cut in half, 7 halves oxygen and only 1 ethane. So I took my delta H. Since I reversed the reaction, I changed the sign to a positive, and then I divided it by 2 because I cut the reaction in half. So there's my delta H for this adjusted reaction. Then the last thing, the hydrogen came from reaction 3. It was on the right side, but the wrong coefficient. So instead of 2, I only want 1. I take that reaction, multiply it by 0.5 or a half. So 2 hydrogens becomes 1, 1 oxygen becomes a half, 2 waters becomes 1. And so I just take that delta H and cut it cut it in half, take half of it. Then when I go to add everything together, remember like terms on both sides will cancel out. So I had 2 plus 1, 3 waters on the product side to cancel out with my 3 waters on the reactant side. I had 3.5 oxygens on the reactant side to cancel out with my 3.5 oxygens on the product side. And my 2 carbon dioxides on both sides, product and reactant, will also cancel out. So I have left the ethene, the hydrogen, and the ethane. That's exactly what I was looking for. So I'm just going to add all of those adjusted delta H values together to get my new delta H. All right, now that may sort of seem like, how does that work? Right? How does that work? Well, it's because when you think about it, in order for these reactions to go, like the ethene has to break the carbon-hydrogen bonds and the carbon-carbon bonds. The oxygen has to break bonds. That is a set amount of energy to break those bonds. And then when you form new bonds, right, an energy is released. So what we're going to do on the next page is start looking at the bonds that are broken and that sort of set amount of energy. And then it might make sense why this all works, Hess's law works. So these are called enthalpies of formation. And these are tabulated. So for your quiz for Chapter 7, right above the credit quiz, there's an enthalpy of formation table. Make sure that you either print that or have that on your screen ready to go when you take the quiz for Chapter 7. These are the kind of things that would be provided, right? But you have to have it in order to answer it. So it says, okay, what is the enthalpy of this reaction here using these heats of formation? So the thing you want to just remember is the heats of formation are given in kilojoules per mole of that substance. So forming water, negative 285.8 kilojoules. All right, so when we do this reaction, we're not forming water, we're consuming water, right? But we're forming ethanol. So what we want to do is when you find the delta H of the reaction, you want to take the sum of the heats of formation of the products, right, using molar coefficients, if any apply, and then subtract by the sum, right, the sigma, the sum of those heats of formations for the reactants using any molar coefficients that apply. In this case, N isn't going to be a problem because everything is a 1-1-1 mole ratio. So basically what we're saying is when we form the ethanol, we release 277.7 kilojoules. We're not forming water, we're consuming water. So we're going to, instead of getting 285.8 kilojoules, we're going to have to put in, right? So we're going to switch the sign of all the reactants and keep the products as is. So products, that delta H of the reaction, negative 277.7 minus, and then the sum of the 52.26 for the ethene added to the negative 285.8 for the water. So first in the parentheses, 52.26 minus the 285.8. I have my negative 277.7 minus a negative 233.54. All right, so now I'm minusing a negative, right? It's going to become a positive. So I'm going to take that 233.54 and add it to a negative 277.7. So I'm going to get a heat of this reaction of negative 44.2 kilojoules. All right. Let's try another one where those coefficients are going to be really important. All right. So first, if you want to do this sort of piece by piece, you can look at your products first if you want. All right, so the heats of formation for the products, I'd have negative 393.5 for the carbon dioxide, but remember that's per mole of carbon dioxide, and I've got 16 moles. Negative 241.8 kilojoules per mole of water, but I have 18 moles of water. So 18 times 241.8. I have a negative 4,352.4 kilojoules, and the 393.5 for the carbon dioxide times 16, I have a negative 6,296.0 kilojoules. So the heats of formation for the products, it's a big amount of energy, right? And that makes sense. It's a combustion reaction. We get a lot of energy. So negative 10,648.4 kilojoules. Now, what about on the reactant side? All right, the heats of formation for the reactants. Oxygen is 0. That's sort of standard state, so no energy, right? So we don't have to worry about that at all. 25 times 0 is still 0. So we're really just looking at the octane, the negative 249, whoops, 0.95 times 2. So 249.95 times 2 is negative 499.9 kilojoules. So now what we need to do to get the heat of the reaction, we take products minus reactants. So our product formation, negative 10,648.4 kilojoules, minus the reactants, the negative 499.9 for the octane. So minusing a negative, right, it becomes a positive. So just adding everything together, we end up here with a delta H of the reaction of negative 10,148.5 kilojoules. So a lot of energy released for the combustion of octane, which is why it's a great fuel for the car, right? We get a lot of energy out. All right, that is the end of chapter 7. We finally got some new material here. So we want to kind of, in an overview, make sure we understand the heat capacity of a system or a substance, right? Is it a calorimeter, or are we looking at like heat absorbed by water, something like that? Then we looked at the enthalpy of a reaction, whether it's exothermic or endothermic. Exothermic means our delta H is negative. Endothermic means our delta H is positive. Then how do we relate that to stoichiometry, right? So delta H given for a reaction, for example, this negative 10,148.5 kilojoules would be the energy released every time I use 2 moles of octane, right? Or every time I produce 16 moles of carbon dioxide. So we learned how to do delta H as a conversion factor in stoichiometry. And then we looked at, okay, if we reverse a reaction, the sign of delta H reverses, right? Positive becomes negative, or vice versa. And if we multiplied through by some sort of integer, like if we cut this in half, we would cut the delta H in half. That was Hess's law. And then the last part here was using enthalpies of formation to figure out the delta H of a reaction. So the idea again here is that when bonds are formed and bonds are broken, right, there's this energy of this that then goes into the overall enthalpy of the reaction. All right, so that is my last part 3. That's the part 3 of 3 for chapter 7.